Awesome. Can everyone hear me properly? Perfect. Welcome to the graveyard shifts of the first day of NDC. Thanks for being here. Really appreciate it. It's for me, coming from Belgium, it's quite late or quite early. I actually have no idea what time it is, but it's always nice to have people at the last session slot of the day, especially in this session. I think it's a nice one. Nice title to it, Sherlock Homepage, a detective story about running large-scale web services. It's kind of a disguised title for a war story on stuff we did on the Nougat server last year, when we had a lot of trouble with frequent downtime, frequent slowdowns of the application, frequent errors that you may have been seeing. And this is basically a talk on fixing those bugs and then falling into the next bug and fixing that and going into the next bug and fixing that again. So let's see if we can dive in. The site is unavailable. This was one of the first items that we had when the site didn't really want to work. So the site was unavailable, and we were seeing that our primary location where we were hosted in Azure was unavailable. So no servers were responding there, and we could not hit the public web endpoint of the server in that data center. So that's not ideal and kind of scary as well. But luckily, we are smart and we have two locations. So we had a secondary location as well, which we load balance to using Traffic Manager in Azure, which means if the primary goes down, the secondary should take over based on a DNS change. It will basically fail for 30 seconds or something like that, but it will fail over to the secondary location. At least we thought, because we saw that the secondary location also was away. So our website was gone from the internet, and that is really, really, really scary if you have a lot of users. So as an end result, our website was down. Now we started looking into it and starting to investigate why or what could be happening. And we saw a couple of things. So the public endpoint of the website was unavailable. DNS worked, but we just could not hit the website through the load balancers in each of these locations on Azure. The funny thing was that the machines were available individually. So if you would hit the specific TCP port where we expose every single machine onto the public internet, we would see that the website would respond normally, and we could generate traffic on it, and everything was working. So that was really, really weird. The Azure load balancer didn't seem to be flowing traffic through, and we were not seeing results for typical users that were not using these special TCP ports. So what could have been going on? Well, turns out we were using a custom load balancer probe in Azure. So what you can do is basically tell Azure where to query every couple of seconds to see if the website is up and running. And if that endpoint returns a 200 OK status code, then Azure will think everything is fine, and the load balancer will keep the machine in the load balancer rotation. The fun thing is, if you start returning a different error code or a different status code, like if error 500 or something, Azure will take your machine out of the load balancer, which is interesting and awesome because you actually want to do that. You don't want to keep your faulty machines in the load balancer rotation. The fun thing happens when all the machines start responding with an error code 500 and all the machines disappear from the load balancer rotation, which basically means that your status check is taking all the machines out of rotation and making sure that the website is just gone if you hit it through the load balancer. So that was what we were seeing. We looked into that and we removed the probe because we saw that all the different machines were responding individually. So we removed this check to basically have a quick fix in getting the website up and running. And the downtime didn't really last long, but we found out that there was some service not responding properly, and some service was basically causing this error 500 to happen and taking the machines out of the load balancer. So this is the implementation of that status service that we were hitting, and we saw that one of these services would be down and causing this error. So either it was our gallery itself which was gone, either it was our SQL database, could have been our storage system, could have been our search service, and could have been our metrics service. So one of these services was down, but we decided to not look into it at the moment the website was down and gone from the load balancer. We decided to fix the load balancer probe and just make sure that we were up and running again. And we were happy because it got fixed. The website got running again, and we were happy, our users were happy, and the fire that was raging on Twitter at that time was cooling down again, which is an awesome thing. Now, how did we find the issue? Why did we come up with, oh, we have to maybe check the load balancer probe there? Well, there's actually a great website called highscalability.com, and I like reading that one because it has technical articles on the big websites out there, but it also has fun parallels with other industries and other disciplines, like, for example, FBI profilers. And there's actually a quote from a book that the guys reviewed, and it says that if you have a crime scene going on, you have to put yourself into the shoes of the victim. You have to know what is going on, you have to learn and feel what is going on with the server or with the service, and know what it was like, and try to build on that experience to find whatever was the issue. So we did that, and thankfully, we knew our service, so we work on the service, so we knew what's happening there. But even then, each one of our team members had a lot of experience with Azure, so we immediately thought that if the website was available on the single instances, but not through the load balancer, the only thing that could be wrong is the load balancer. So you have to know your system. You also have to have some logging and telemetry, of course. But it's the combination of all those things that makes you appreciate your system, know your system, and fix whatever is wrong with your system. So with that, thanks for being here, and thanks for joining this presentation. As I said, I'm from Belgium. I just took a nap before the session, which is awesome, but I don't think it's a good idea to have done that because I don't know what time it is right now. If you look on the map, I'm from Antwerp, which is a nice city in the north of Belgium. We have awesome chocolate, we have awesome beers, and it's a great place to live. I work in the Microsoft's on the Nougat team, so I'm a developer on the server side there, and as I said in the introduction, this talk is going to be mostly about how we fixed the Nougat website. So let's give you a bit of history and context on our application, so you also have the knowledge of how our application was built and structured at the time we had all these issues happening. So the Nougat website, if you don't know Nougat, who doesn't know Nougat? Okay, good. We serve dependencies for .NET developers worldwide, and pretty much every developer is using us continuously during their day-to-day job, installing packages, updating their dependencies, and so on. So we get a lot of requests, and at the time all these things happened, we served around 8 million to 10 million requests per day on our compute nodes alone, because we also have a lot of things that are just served by storage and a CDN. So we have quite a number of users on compute during the day. Nougat was built 4 to 5 years ago, and at that time it was really hip to expose your data as an OData service. And OData is basically an HTTP protocol that allows you to expose a queryable interface over HTTP. And as Microsoft released OData, they started to do a lot of samples, and all those samples were basically just exposing the raw SQL database over HTTP. And Nougat, of course, did that as well because it was a nice sample and a nice showcase of the technology. Problem with that was Nougat started to grow, and a lot of things had to happen over the years to make it perform, because pretty much every developer was just hitting our database and running queries on our database. So that's not the best technology to work with. It's a monolithic site back then. We had our web application, so if you go to nougat.org and want to publish a package or search in your browser, that's the exact same application as the application that is serving the OData queries that Visual Studio is using to install the packages in Visual Studio. Some improvements have been made. So the SQL database is no longer hit for every single query that you are making to this OData endpoint. But yeah, we had some rough times transitioning from that period of time to where we are right now, and that's this session. So the architecture back then was, we had some front-end servers in 2 regions, 2 Azure data center regions, and that front-end website is hosting the MVC application as well as the OData service, which is a WCF service. Those front-end servers are backed by a SQL database, And that database contains all the package metadata. So if you search for a specific package, the package ID, the package description, tags, and things like that would come from this database. The database is also used to track download counts. So whenever you do a download of a NuGet package, NuGet would write to the database saying, okay, this package has been downloaded one time. It was this specific client version, it was this user agent, this was the IP address and the geolocation of the user, just to have some metrics on who is downloading everything. So that means that if you would do a download, you would query the database to find that metadata and serve that metadata, but you would also push an update into the database because you were increasing the download counter there. Now, we did some improvements because searching on the database for every single query on NuGet was not that performant. So we built a search service, which is a Lucene-based search service that contains all the metadata of the packages. And if you use Visual Studio to search for a package, you're actually hitting that search service directly with Visual Studio 2015, indirectly with Visual Studio 2013. Because we basically linked the WCF OData service to this search service so that whenever you would hit the search service on the website, you would actually hit this Lucene index to take the load off of the database. Now, of course, this search service has to get its data as well, and that data is on Azure storage, just raw blob storage. We have the Lucene index running there. And that thing just uses that to search, to serve the search results and serve things like download counts and so on. Now, of course, the data has to flow between those things, and we have a number of background jobs as well. And these background jobs basically read the database, build an index. Whenever you publish a package, for example, the package gets added to this index and just flows through that entire system to this search service. So that's roughly the architecture back then, last year, around March to May timeframe. So did we solve the crime? Did we actually solve this issue we had with the load balancer in the beginning of this session? Well, we didn't really do it. We removed the load balancer probe to get the servers back into rotation, but we didn't actually fix or find the root cause of what was happening here. So flashback to our issue we had. The load balancer was taking each server out of rotation because our status service was responding with a error 500 status codes. And that status code was there because of one of these services. Now, we could rule out one of them because the status service was also checking itself. And if it could check itself, that means that the status service is up. So it's a stupid redundant check, but we basically found 4 possible root causes of this issue where the status service was returning an error 500. So it could have been SQL, could have been a database, could have been storage, could have been our search service, or could have been our metric service, which basically takes all the download counts and does this increment by 1 whenever you download a package on NuGet. So one of these services was causing this issue. So we looked at all our logs, for example, the SQL database logs, and we found the database had just been running perfectly fine, we think, because we didn't have all the logs back then. So that's another nice thing to discover when searching for the issue. We found we had no detailed logs on whatever was happening on the database back then. So we fixed that along the way, but we were fairly confident that the SQL database had not been acting up and had not been causing the trouble. Especially because all the different individual machines were still reachable and we could run queries on them. So that basically meant that the database was fine and just returning results as we were expecting. Storage seemed stable as well. We had lots of logging there as well, and we saw 100% uptime, no latency issues, no dropped requests or whatsoever. So unless our logs were lying to us, storage was not the issue there. We looked at search. And search had just been running for a couple of months just fine, no issues with it. And in the logs there, we also didn't really discover anything significant that would explain this status service to be down. We looked into our metric service, which is like the simplest REST API you could have. It's just posting data to an HTTP endpoint, and that the HTTP endpoint would increment the download count in the database. So nothing really special going on there. And we didn't really find anything obvious in any of the logs of these different 4 services that we were calling. So we started looking around at the crime scene itself. We started pulling IIS logs. We started looking into Event Viewer. We started looking into a lot of things. We even started profiling on our production servers because we were stunned that there was no information in any of the logs, and we just wanted to find out what could have been the cause and could have caused this downtime. So we started profiling the website, and we did that, as I said, on production, which is something you probably don't want to do, but it was our last resort, and we had to dive into that. So we did some profiling there, and we saw a couple of things. First of all, let me start zoom it. First of all, we saw that there was a little bit of blocking garbage collection, like 2% of the time we had blocking garbage collection. It's not too bad, it's not good either, but nothing special going on there. We saw a couple of methods there. We saw that the, can't zoom in to there. We saw that the hijack method here was hit 9% of the time. So it turned out that our hijack that we do when you hit the OData endpoint and we redirect you basically to the search service, 9% of the time was spent in this hijack, and we started digging in there, and we saw that hijack was called quite a lot of times, which is as expected because we redirect to the search service because we wanted to offload the database, and we didn't really find out anything interesting here. Yeah, there's this garbage collection that's happening, but it's not out of the ordinary, and it's not something really, really special. So our gallery was definitely not the cause. There was some room for improvement. We actually went into this profiling report, and we found a couple of things that could be optimized, but nothing that would explain the downtime that we saw. So yeah, that's nice, but we were still left with nothing because we didn't know why our website was down the previous day. So it could have been search, because we saw all of this traffic going to this hijack method, which would redirect to the search service. But again, the logs didn't show anything, and this gallery profiling on the web servers in front of it didn't really show anything special either. So yeah, we continued the chain and started profiling our search service as well. And our search service proved a little more interesting. If you look at these things, log contention, for example, we had 16% of the time our search service was waiting for logs to be released. That's something you don't really want to have in your application, because it means your users are waiting a lot of the time for logs to be released if this is in a request path, for example. Another interesting thing was that we had 58% of the time blocking garbage collection, which means that our server was doing more work in garbage collection than in serving requests and responses back to our users. That's not something you want to have in there. So let's dive in there and select this log contention and see what's happening. So an interesting thing we see here in this chart is that the log contention basically happens when we are not garbage collecting. So this brown chart is the garbage collection happening. It happens here as well. So either we are garbage collecting, or either we were waiting for something to happen or waiting for a log to be released. So this is not a healthy application, and we got really worried about this because the search service looked like the culprit and the thing that was actually causing this issue that we had previously. So we went in there, and looking at the top methods that were being called, we saw this searcher manager.get, and I can't zoom to that corner of the screen, which is really, really funny. But I'll do it like this. So we saw that this get method was being called 59% of the time, and a release method was called 38% of the time. Interesting, because those two methods were basically whatever our search service is doing. So whenever we do an index reload, whenever we load the search index again from storage, these two methods would be called. The get would be called to load the index, and release would be whenever the index has a newer version and we release the old version back to the system. So these two methods were actually causing either garbage collection or waiting for logs to be released. So we started looking into the code, and this was a deployment that happened long time ago, and we didn't really have the codes anymore. So we had to download a decompiler to look at our actual production code that was deployed at the time. And we started digging into that, and we found a couple of interesting things. The searcher manager that we use, which calls this get method to load the index and release the index afterwards, was checking Lucene index freshness, which is perfectly fine. You want to check if your index has been updated, and if it has been updated, you want to reload it so you can search the new results that are in that index. The big issue we had there is that in the start reopen method we had, when you would start reopening the index from storage, and actually have a link to GitHub from that time, we had this happening. So we had a lock there, and while the reopen was happening, we would just wait until the index was reloaded and then continue and free this lock and make it available to the search service. So this thing was actually causing our downtime because loading our index would take around 2 minutes at that time, because it was quite fragmented and stuff like that. So we would just wait for 2 minutes in a request path for this lock to be freed, and that was horrible. So we fixed that. We took this guy out of the request path. So we created a background job that would reload the index and swap the index that was being used to serve searches. But we learned the hard way that this is not something you want to do in your request paths. Now, was this in the request path for every user that was hitting the search service? No. Where we were doing this, where we were checking if the index was still fresh, was in our monitoring. So our monitoring would call a specific endpoint on the search service. The search service would then check if the index was to be reloaded. It would start to reload, wait for 2 minutes, and then free the lock. Problem is that same lock was checked in the request path, so if our monitoring would take long, requests would take long because the lock was not being freed and people would just have to wait for that lock to be freed again. So we fixed that. We took that out of the request path and moved it into a background job so that the lock would never hurt production traffic or never would hurt any HTTP requests coming in. So awesome. Now back to the profiler, we also saw this garbage collection issue. We found out a lot of this garbage collection was caused by loading the Lucene index. It would just reserve a big chunk of memory in our .NET runtime and then free it again. But we also saw that Newtonsoft JSON.NET was actually causing a lot of this memory traffic. I see. Yeah, we had a lot of objects that were really causing an issue here. So what would happen if we did an index reload was that we would also reload the number of downloads packages had, because the package download count actually influences the search results. So we have to know how many times your package has been downloaded. Now, if we would increment this number in the index, that would mean we would have a really high index churn, because you would actually have to delete and reinsert the documents into the search index. And you don't want to do that for every download or every 10 downloads or even every 100 downloads. So what we did was instead have a background process, created a big 12 megabyte JSON blob which contains package ID, package version, and the download count. And whenever the index would be reloaded, we would also reload that specific blob and load it into memory and make sure that we could use it. Problem was, as we saw later in a memory trace, that this loading of these download counts was actually causing a lot of memory traffic. It was causing the garbage collector to have a lot of work. The garbage collector had to do a lot of work. And why was that? Well, turns out we were loading all this data into 2 dictionaries. So we had a dictionary that had a key of the package ID and a value of the list of versions and their download counts. But we would, whenever we loaded that JSON blob, we would recreate that entire dictionary in memory and just discard the old one, basically give it back to the .NET runtime. So .NET would have to reclaim a couple of million objects in memory every time we did that reload. And that was causing this garbage collection traffic, memory traffic and the garbage collection issue. So what we did was we started reusing that dictionary. So instead of recreating the dictionary whenever you would deserialize the JSON data, we would just reuse the dictionary and update all the existing values in the existing dictionary, because the package IDs typically don't really change. The only data that changes is the download counts, and even that doesn't change that often for most of our packages. So we basically decided to stream the entire JSON blob and just update the download counts in the existing dictionary if the package was already in there, If not, we would just add it and not cause a lot of memory traffic. Another interesting thing we saw was that there were a lot of strings loaded in memory as well. Reason for that was that we were also using JObject.parse, which means you load the entire string, the entire blob into a string, then deserialize the entire thing into a JObject, and then use that to populate the dictionary. Well, turns out that's also not a good thing to do if you have this 12 megabyte blob containing JSON data. Better thing is to just stream over the entire file and just load basically package per package, package version by package version, and reuse these objects and not instantiate objects all the time in there. So we fixed that, and we were happy because we found a really nasty bug in our search service, and we thought, okay, we're good to go for another year. Well, turns out that was the case, but not for a year, but for a couple of weeks. In those weeks, we did a couple of things because we discovered we didn't have all the logging we really wanted to have. So we added additional monitoring, additional tracing. We started looking into App Insights as well. I don't know if you're familiar with that product. It's basically sort of like a mini continuous profiler on your application that collects request data, couples it to stack traces, couples it to exceptions, and so on. So you can search in it and basically troubleshoot your application more easily. So we started investing in that, did a lot of changes there, and we're confident that whenever something would happen, we would have the data to investigate it, and we would no longer have to recite to profiling on the production system. So as I said, a couple of weeks later, we started seeing another issue on our services. We were starting to see internal server errors whenever people would do package restores. Search was working fine if you had existing packages and would just want to check for updates, for example, that would work perfectly fine. The only thing that was not working was if you open up a solution and you don't have the packages on your system and you would want to download all those packages to your system, that would fail with an error 500 as well. What we were seeing in App Insights was that the response time would go up. The number of requests would actually be stable or go down even a little. The exception rate would not really go up. It was just the response time that was going up. So yeah, that's an issue. So what we did was we looked into the traces we had in App Insights. We started looking into the events that were being logged in the Windows event log, and we saw that IIS was crashing during these time frames. So whenever this response time would go up, we would see at least one of our servers having an IIS crash, restarting the application pool and returning error 500s for a couple of seconds. So that was what we were seeing there, but what was the cause of that? So we started looking into all of our logs, and we didn't really find anything significant, except for the fact that we saw that IIS was crashing on us. We saw that on our storage accounts. We saw the crash dumps of IIS being written, so we saw quite a number of crash dumps on there. So that confirmed that IIS was crashing, but didn't really tell us what the cause of that crash was. We also started looking into the http.sys logs on our web server. http.sys is basically the HTTP subsystem you have in your Windows machines. So whenever you use IIS or even a self-hosted web application, you're actually using http.sys as the web server, and IIS is just a fancy, expensive, nice wrapper around this http.sys. Now, IIS has logs, but http.sys itself, this kernel module handling HTTP traffic, also has logging. And we looked into that one, and we saw a tremendous amount of connection abandoned by request queue type of errors. So if you look up that error, you will see that it actually means that the application pool just stopped working unexpectedly, which typically denotes a crash has happened. So all those things combined told us, well, the root cause of this thing is going to be IIS crashing out on us, and we wanted to start looking into those crash dumps. So we loaded those crash dumps onto our machines and started looking into them. Now, hardcore debuggers will typically use something like WinDebug or something, but if you have a crash dump, you can actually open that crash dump in Visual Studio as well. And that's a nice thing because it gives you a number of things in terms of information. I don't know if you're familiar with crash dumps. You basically have two different types of crash dumps. One of them is a full dump that contains stack traces, exceptions, and whatever is happening at the time the crash dump is created. The other one is a mini dump, which just contains the stack traces, but not whatever is in memory at the time. Azure, for us, was creating mini dumps, so it meant that we had stack traces, we knew which threads were running, which methods were running, and things like that, but we didn't have the actual values of the variables in memory. Still quite interesting, because when we opened this crash dump, we saw that the thread tried to read from or write to a virtual address for which it does not have the appropriate access. That's a nice error. I don't know if you've ever seen this one. I hadn't seen this one before. And turns out it's quite an interesting one to debug as well. Now, if you open a crash dump in Visual Studio, you can actually tell Visual Studio to act like it is debugging connected to the process that is running this thing at the time this crash dump was happening. So let's debug with managed only. And if we do that, we will typically wait for symbols to be loaded. And I found out that Australia apparently is far away from the Microsoft symbol servers. So let's see how fast this goes. This is actually not bad. I did this in the room before, and that was terrible. So this is quite okay. Won't be long. Should not be long. The thing we will see is that the exception that happened at the time the crash dump was made will just pop into our face and show the cause of the error on the server. So let's wait for symbols to be loaded. There we are. We see the exception. This time we see the exception with both the message as well as the memory address where this happened, the module in which this happened, and so on. So let's break. And if we break, we can actually close the threads window. We can actually look at the disassembly of this code. So let's disable just my code, and let's look at the disassembly. And apparently the issue was this move statement in memory. Awesome. But yeah, what was going on in the application? So an interesting thing you can do is if you have a crash dump and you have the symbols of the application and the assemblies of the application like it was built on your CI system, for example, you can actually load those symbols and look at the source code of this entire thing. Now, the problem was that at this point in time, we discovered our build server was not storing symbols, which meant that this deployment we had crashing on us. We did, of course, have the assemblies because the assemblies were serving the application on the server, but we did not have the debugger symbols on our build server, which meant that the only thing we were left with was this disassembly, and that didn't really tell us a lot. So luckily for us, we still had the assemblies, of course, and JetBrains has an awesome decompiler, and you can load the assemblies in there and look at the code. So for example, I loaded the assembly which crashed on us, and we can look at whatever is in there. We can look at all the different MVC areas. We can look at the controllers and search through that. But a more interesting thing is that .peak also comes with a symbol server. So if I enable this little button there, it will host a symbol server for us and actually mimic the Microsoft symbol servers or whatever symbol server you would have, decompile everything on the fly and serve that data to Visual Studio, essentially giving us the source code of the application that was running at the time. So let's do that. Let's dive back into Visual Studio. And this time set the symbol path, includes our .peak as the decompiler. Also, yeah, that one was disabled. And if we do this, we can debug again, and this time we will get much more information because Visual Studio will reach out to .peak, which will decompile the actual assemblies that we had back then, and will show us the source code of the application as it was when this error happened. So here we are. We see the exception, and we actually see the line of code where this happens. Now, be warned, this is not the actual code that you wrote and that got compiled into the application. This is, of course, decompiled code, and it's compiler optimized, and it's not exactly what you wrote, but it should give you a good idea of what was happening in the application. And apparently, our post-download statistics methods, which would track a download whenever you would install a package, was failing us. Now, as I said before, this is the metric service, and that metric service is really, really stupid. It's the simplest service you've ever seen. So we were kind of surprised that this method was crashing on us. Even more, you see that we do a task.run and just fire and forget basically to increment the download counter. So we were not expecting that a task.run would actually cause IIS to crash, because we would simply fire and forget, and even if the download count wasn't really tracked, we don't really care that much about those download counts at those moments in time. So we would expect this to just work and never, 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 never crash our IIS in production. But turns out it did crash IIS in production. So we started searching the internet. Bing didn't find a lot of things because, yeah, Bing is an awesome search engine for some things, but for technical topics, it's not always the best. Turns out Google was also not really helpful, because we didn't find a lot of information in there as well. We searched on the error message, where we had this, the actual error message. That gave a lot of results, but nothing that related to our codes, nothing that related to the scenario that we were seeing. Until somewhere on page 50 of some search engine, we found another person who had an unobserved task exception when doing this fire and forget type of operation in his application. So we looked at that link and we started reading. And basically what the guy was saying was that if you do a task.run and just fire and forget the operation in there, and that operation crashes, the exception will actually bubble up, and if no one catches the exception, your process will die. And that was what was happening. We did not really catch that exception because we were just expecting it to always work, and even if it would not work, we did not expect that the exception would bubble up, yet it bubbled up and basically crashed IIS whenever updating the download count went wrong. So turns out the fix is quite easy. All you have to do is tell the task scheduler what to do whenever you have an unobserved task exception, and tell it that the exception was handled. So we added this portion of codes, handle the unobserved task exception, we log it, we track the metrics in it, and then set it observed, and IIS was perfectly fine with that, and would no longer crash on us. Awesome. Case closed, another issue down, and we thought, we're good for another year. That was a colleague of mine, by the way, who had a witty remark on that. Anyway. So we thought we were good for another year, but apparently a couple of weeks later, we saw another issue arise on our services. We saw high response times on the web server in general. So basically, any request that would happen would have really high response times. So what we were seeing was high response times, lots of CPU usage on the servers. We saw that Azure was auto-scaling. So back then we had Azure auto-scaling enabled based on the CPU percentage, which would mean if the CPU would max out, we would just add more instances, hoping that this would be able to serve or handle all the traffic. Of course, it didn't. It would just spin up new service and also max their CPU out. So we were seeing that. And when profiling it using App Insights, we did not really see the root cause of what was causing these high response times. So we basically started looking into our logs. We started looking into App Insights. We started looking into all the logging we had. We started doing Google searches on whatever could be causing unexpected rises in response times. And what we found was what we thought the root cause of this issue. And it turns out it actually was the root cause of this issue. Turns out that if you are using IIS to serve your traffic and you have lots of requests coming in, IIS will handle them just fine. IIS does have an issue, which is that if you have burst requests coming in, which means you have a low usage of the service at one point in time, and then all of a sudden the hordes would come in and start hammering your server, IIS does not really like having that. Reason for that is IIS has this concept of worker threads, which handle the requests that are coming in, but also IO threads, which do things like communicate with the database or communicate with the storage system and stuff like that. Whenever IIS starts your application pool, it will fire up a number of worker threads to handle HTTP traffic coming in. And by default, it will start, I think, 2 I/O threads per CPU in your server to handle things like database communication and storage and things like that. Whenever traffic comes in and traffic increases, IIS will dynamically detect that it needs more threads to handle all the traffic, and it will, for example, scale to 10 I/O threads to do database communication and stuff like that. The only issue is that IIS has to learn about what is happening, and it has to see that the traffic is slightly increasing and slightly going up. But if all of a sudden you get this burst of traffic, IIS will simply add 1 thread or 2 threads, but not the 10 threads or the 100 threads you would actually need at that point in time. So IIS would eventually scale up to the point that you wanted to scale up to, but not immediately. And that was actually causing these high response times that we had there. And turns out the fix was actually quite easy. We would just have to change the default settings in IIS to spin up more worker threads in the background, so that even if we would have bursts coming in the requests, IIS would have enough threads to handle database and storage and stuff like that. So the results, we had App Insights, and you would see that the application would spike in request times. We turned on this setting, and immediately you see the drop to something that's almost a flat line in response times. And yeah, you can really see where we did the change and where we optimized this minimum I/O threads. Nice side effect was that our server response time went down in general as well. Why? Well, we had auto-scaling, we had a number of servers, so not all servers added the exact same amount of I/O threads. So you would always have a couple of servers that would be slower or responding a little bit slower. But by changing this setting, all the servers were on the same page whenever they started the application pool. And we immediately basically saw that the response times would drop to a constant level on all machines at all time. Awesome. Now, Azure is quite nice if you're hosting on web roles. You can actually RDP into the machine and make changes to IIS to, for example, change this min I/O threads setting. Problem is, if you do that, the next time you do a deployment or the next time Azure decides to kill your machine and reboot it on a different host, those changes will be gone. So you have to somehow make it permanent, and the way to do that in Azure is by creating a startup script. So what we did was add a few lines of command line codes to our application so that on every deployment it would call into the command line IIS configuration tool and set these worker threads to a reasonable number instead of the default. Awesome. Case closed. We're good for another year. Well, turns out we were not good for another year. It turned out we were good for another 4 hours, and after that, a little more, but still. It turned out that we were seeing package restore timeouts. So we optimized a number of things. We were seeing that response times would drop to a pretty much constant level, yet we were seeing that package restores were timing out. And again, only package restores, so bringing down the packages whenever you don't have them on disk. Everything else would be just working fine. So here's what we were seeing. On the V2-based feeds, so basically Visual Studio 2003, 2013, and the first versions of 2015, they would hit our .cf OData service. That one would hit the get method, where you would get by ID and version to get the metadata to see if you can actually install the package and get the download URL to the package. And what we were seeing is package restores on that specific call in the service. We were seeing this every 7 to 15 hours, so not continuously, every 7 to 15 hours, and it would last for 10 to 15 minutes, and afterwards everything would work just fine again. So very temporal, very, not really easy to debug and not really easy to trap what was going on. Nice screenshot from App Insights. If you were doing package restores, we actually had requests take up to 1 minute to serve a package, which is insane for something that just fetches metadata from the database by ID and version, so primary key lookup, and would give you a URL to where you would actually download the package. So 1 minute for that operation is just crazy. We didn't really see an easy way to reproduce this issue. It was happening only on production. We did our best to reproduce this issue on our development and our staging environments. We weren't able to do it. Why? Because we weren't really sure what was happening, because it would only happen for a couple of minutes every couple of hours. So it was really hard to reproduce, and we RDP'd into our production systems. And we basically had someone on the team look at this, at the task monitor for the entire day, looking at when the CPU would spike to trap the issue and try and get some information about what was happening in the process at the time. And what we were seeing was high CPU load whenever this would happen. But we had no way to continuously profile this because profiling generates a lot of data, so it was really difficult to trap whatever was going on there. So we looked at what we did recently to fix things, and we thought, okay, so we changed this min IO threads value to make sure that whenever requests would come in, IS would have enough threads available to handle things like database and storage communication. And the slow code path is find packages by ID. So we started looking into what this method actually does, finding packages by ID. And what it does is it reaches out to the search service, which is a REST-based service, so over HTTP, to basically fetch the metadata of that specific package and serve it back to the user. So what could min IO threads and max IO threads in IIS have in common with HTTP calls being made in the application to a different service? We did a lot of searching again and a lot of research again. And we found an interesting article that basically benchmarked HTTP client, so the .NET HTTP client that you can use to call into any service out there. And we found out that if you use HTTP clients and its async model of programming, that HTTP client doesn't really limit the number of concurrent requests it makes on your server. So what we were seeing was if people would start doing package restores, there's typically a lot of requests coming in because every package in your solution would be checked if it's still on Nougat and where it could be downloaded. And typically, whenever the US wakes up, for example, you would see a lot of traffic coming into the service. And evidently, this service would make a lot of calls to our search service in the back. So what we were seeing, we thought, was that the HTTP client would just hammer our search service. Our search service would be perfectly happy with that and serve traffic, but still somehow it would block on making those requests at a certain point in time. Reason is that HTTP client does not limit the number of concurrent requests it makes to an upstream service. Combine that with the fact that the number of TCP ports you have on a machine is limited. And combine that with the fact that you are running on a web server, which means that you have TCP ports in use to serve your clients, and you have TCP ports in use to basically fetch data from this upstream service, makes that you're actually using a lot of TCP ports on the system. You would think those requests are quite fast and they would free up again after the TCP port has been used by the operating system or by the .NET runtime. Well, turns out that every TCP port that you use to make an upstream connection or a downstream connection is being held for about 4 minutes by the operating system to make sure that whenever a request still returns or there's traffic returning to your service, to make sure that doesn't confuse the runtime because the request was already handled and some router in between is resending packages that have already been received. So combine all that information, and if you do a quick calculation, you will find that you can pretty fast, you can starve the number of TCP ports you have on a server pretty fast, actually. So we looked into why this was happening and what we could do to limit the number of concurrent requests this HTTP client could make to upstream services. And we found that if you don't set the service point manager.default connection limit to a reasonable value, you would just starve your TCP ports on your system. So all we had to do basically to fix this issue was set a value to that thing, and .NET would simply respect whatever value we set there and have more than enough TCP ports and reuse them and work fine. So that's what we did. We changed a few things in our codes and we set the maximum number of concurrent requests that could be made. Now, when reading all these blogs and articles and internal documentation, we also found out there's a couple of other optimizations that .NET does for you that you typically don't want to have if you have a server-side application that makes upstream calls to a really tiny service that returns small amounts of data. So another thing we disabled was nagling. And nagling is an optimization in the TCP/IP protocol that basically combines several smaller requests into one TCP packet so that you would not be flooding the network with small packets and instead would just put a lower number of packets on the network. So we disabled that because it didn't make sense to do that because all of our requests would typically be smaller than a number of TCP packets. So we disabled it to make sure that, yes, the network would be flooded a little more, but traffic would flow faster back and forth between our search service and the gallery. So we did that, and we also disabled expect 100 continue on this thing to basically make sure that the TCP connections or the connection would be freed up faster on the server there. Some charts after optimizing this. So remember that we had 1 minute of response time for a package restore. Well, when we enabled these changes, you could really see a drop in the response time back to a normal level. You could see the number of requests actually go up a little bit, so the server was able to handle more traffic by making this change, and response times would drop to their normal levels, around 3 seconds for some, or at least the highest number, the highest response time in there. Still not really, really good, but much, much better than 1 minute, of course. Awesome, case closed, good for another year. Yeah, so we thought that again, and we started thinking like, okay, good for another few weeks probably. And yet again, by fixing a bug, we actually uncovered another bug in the system. So we were seeing memory pressure. What we were seeing was on all the different servers we were running, we would see 100% CPU usage. Being developers and being developers using a cloud service, we thought, okay, we are Microsoft, we actually pay these services internally at internal rates, so let's go for bigger VMs. So we increased the size of the VM, and what we saw was that the bigger VM was also spending 100% of its time, 100% of CPU, of memory. Awesome, maybe we don't have enough memory in those bigger machines, so we went up another level of machines. So we basically did our memory on each instance times 4, and what we saw was, again, 100% of memory usage in there. So if you do that a couple of times and you keep on doing that, that's just stupid. So we thought, okay, we did it twice and we saw the same result again, so probably the application is misbehaving here. So what is eating that memory? So to discover that, you actually have to do some memory profiling, and you have 2 places where you can do this. On production, which we did not really want to do again, or try and reproduce it on a test server and profile on that test server. So we decided on the latter and download all of our IIS logs and replay traffic onto a server or onto a spare server and attach a profiler on that machine. So we did that, and we downloaded all of our IIS logs. And our IIS logs, where do I have it? You can actually load those into a nice tool called JMeter. It's an open source tool which is written in Java and is very high DPI friendly, as you can see. But it's actually an awesome tool because it allows you to read a web server log, specify a number of threads to cycle through that entire log and replay traffic onto a different server. So what we were able to do is just take actual HTTP logs from our production machines and replay it using JMeter. You can actually have multiple agents putting traffic onto your server. So we were actually able to reproduce the exact amount of traffic and the exact traffic flow that we had on production onto our development server. So we did that and attached a memory profiler. Now, before we dive into the actual profiling of memory, I just want to give you a quick introduction into memory management in .NET. Who of you dare say they are really familiar with how .NET does its memory management? Like, I guess no one really, everyone knows a little bit, and I also know a little bit, so let's put out a baseline there. So when you allocate memory in .NET, what is happening is that you are not doing something like C++ would do, ask the operating system for a portion of memory in its address space and use that. what you do is actually you start the application and .NET will reserve a massive chunk of memory for your application, and .NET will simply allocate your variables in that block it gets from the operating system. And we're not using that memory anymore. .NET will free that memory for you. That thing is called the managed heap. So whenever you allocate a new object, whenever you create a string or create a new object or a person or an address or whatever objects that you are using, you're actually allocating that object in this managed heap, this .NET memory space. Now, it's really fast to do that because .NET doesn't have to go to the OS to ask for additional memory. It just has a block and it can freely allocate itself. Of course, .NET also uses some unmanaged memory for doing things like hosting its own memory, hosting the garbage collector and things like that. But generally, you have this managed heap and all your stuff goes in there. Of course, all your stuff has to go out of there as well if it's no longer being used. In C++, for example, if you ask memory from the operating system and you no longer need it, you would give it back to the operating system so it knows it can distribute it to another application or maybe again to your same application. .NET does not do that. .NET has its own memory space that it freely distributes and allocates for your objects in the .NET space. And it has a garbage collector instead. So what will happen is if your variable is no longer being used, .NET will simply scan the entire managed heap, look at the objects that are in there, and if it finds something that is no longer being used, it will kill it and update it in its own index basically to be able to allocate that memory for new variables in your application again. Now this managed heap is divided into multiple generations. You may have seen Gen 0, Gen 1, Gen 2 and stuff like that. Reason for that is a lot of objects are really short-lived. Typically you have a method, you allocate a variable, and at the end of the method the variable is no longer being used. So there's no point in keeping that variable around or keeping the memory space around. And Gen 0 is basically where all objects are allocated whenever you allocate something in the .NET memory. Typically, garbage collection is really fast because if .NET wants to free up some memory, it will simply scan that Gen 0 space and remove everything that's no longer being used. If something is still in use, whenever that garbage collection cycle happens, .NET moves the object into Gen 1. And same thing happens there. .NET will scan Gen 1 for objects that are no longer being used, and if that's the case, it will remove the object. If it's still being used, it will go to Gen 2, where it will just keep on living or eventually be cleaned up again if it's no longer being used. Now, why these generations and why this moving of objects between those generations? Well, the reason for that is typically if you have short-lived objects, they don't have a lot of pointers to them. They are being used in one method and there's only one pointer. So it's really easy to free it up by the garbage collector, and the garbage collector can simply scan the entire thing and free up the memory there. Now, of course, if you have an object that lives longer in this managed heap, then there may be more pointers to this specific object, and the garbage collector may have to do much more work to find out who is actually using that specific object and to see if it can actually free up the memory or not. Same thing with Gen 2. If you end up in Gen 2, you actually have an object that lives quite long, and the garbage collector has more work to check if that object is still being used or not. So what that .NET does is it keeps these generations. Long-lived objects go into Gen 2, medium-lived objects go into Gen 1, and short-lived objects just remain in Gen 0 and get cleaned up in there. That's one thing, to basically partition the memory like that. The second reason for that is that the garbage collector has a lot of work to basically check all these pointers, and it checks Gen 0 more often than Gen 2, because .NET is smart enough to know that in Gen 2, if your object ends up in there, it's longer lived and it will not have to check that every couple of milliseconds or every couple of seconds. It's usually good to check it less often to see if those objects can be freed or not. So that's what happens there. So in a nice diagram, you basically allocate an object in Gen 0. If it's still being used, it moves to Gen 1. If not, it gets freed. In Gen 1, a garbage collection cycle may happen and the object may move to Gen 2 if it's still in use. If not, it gets freed and perfectly fine. If your object is in Gen 2 and a garbage collection cycle happens there and the object is still in use, it will just stay in Gen 2. If not, the garbage collector will free it up. Now, when does the garbage collector run? There's some documentation, but not all the documentation is as clear as you would like it to be. Generally, when does the garbage collector run? Typically when you have an out-of-memory situation where you have memory pressure and your .NET runtime needs additional memory to host your application and to allocate variables. That's typically when garbage collection would run. After you do a lot of allocations, the garbage collector will typically run as well. Remember where we were reading all this JSON data and making sure that we could deserialize it into a dictionary? Well, that was a significant allocation because we were allocating millions of objects in memory. Typically, the garbage collector would run on such a situation. You can attach a profiler and tell the garbage collector to run. You can have the garbage collector run when the application moves to the background. So there's a number of reasons why the garbage collector may run. But I'm saying may run because the garbage collector is not guaranteed to run. So it may well be that you just allocate memory, and if there's memory enough or none of these conditions happens, .NET will simply not run the garbage collector and not free up memory because it's not considered necessary. Why not? Well, the garbage collector takes some time, it pauses your application, it actually causes a small slowdown whenever it runs. So when it decides it should not run, it does not run. Just not have that pause in the application. So with that knowledge, let's dive into our memory pressure where we were seeing 100% memory usage on a small server and on a large server. So what we did was profile reproduce traffic on a development server and attach a memory profiler to it. And we took several snapshots during that process. Now I'm going to open this specific snapshot, snapshot number 6. Reason for that is that it turns out that the garbage collector ran here. So we see that this snapshot has 2 million objects less than the previous snapshot, which means somewhere in between the garbage collector has run, has done its thing, and this snapshot would contain the objects that were not being freed. And that's what we were interested in because we saw memory pressure, which means something sticks in memory and is not being freed up. So we want to know what that is. So let's dive into that one. And we can see a number of things like the largest size of objects that is in memory. We see a lot of strings in there. We see a lot of string duplicates and things like that. But nothing out of the ordinary, and this profiler doesn't really give us a clear indication immediately on some common things like event handler leaks and stuff like that. What we can see though is that if my zoom it works properly, what we can see is that Gen 2 is actually quite full. There's a lot of objects in Gen 2, which means that we have a lot of objects that are not being garbage collected. So let's dive in there and look into what is happening in there. So Gen 2, awesome. Let's dive into that one and see which objects are in there. And what we can see is that there's this ninject.activation.caching.cache, which has, it's really annoying that zoom it doesn't really work properly. Let's try it like that. What we can see is one of those objects, small object, but it's the object retaining the most memory in our .NET memory space. This thing has some other things, but yeah, we're using a dependency injection container, so it's probably fine that we are doing this. A more interesting thing is that our entity framework context is around in memory for 827 times. That's not too bad because we have a lot of traffic on the server. What is bad though is that we are looking at Gen 2. So this means that our entity framework contexts are long-lived and are not being collected by the garbage collector. That also is not that much of a problem, but keep in mind if you are using entity framework, that entity framework is tracking changes to the objects that have been loaded. So this basically means that all these entity framework contexts are dragging along domain objects from our application because it still has the change tracking enabled for all those things. So this means that we're using quite a large number of memory in Gen 2 by just having objects that are probably no longer being used because we have request response cycle and you typically don't end up in Gen 2 doing that. So let's dive into the entity framework context. And what we want to see is which object is holding on to these entity framework contexts. So what we can do is group by similar retention, and we can actually get a nice diagram telling us where the entity framework context is being held in memory. And if we look at that diagram, can't really zoom in properly. Let's try again using this one. If we look at the diagram, we can see that it's being held in memory in a dictionary somewhere, and that dictionary comes from a cache, and that cache, if we dive into that one, is our dependency injection container. Awkward. Our dependency injection container is keeping around entity framework context for a long period of time, and they don't get collected and memory simply fills up. Interesting. So at the time, we were using Ninject as our DI container, and we started looking into the source codes of Ninject to see if we could actually find an explanation why these entity framework contexts were being held in memory. So we found out that there was this garbage collection cache pruner object, which is actually the object responsible for freeing up the memory that Ninject is using. And if you look at the code of that thing, it's actually quite clever, or at least the implementation they did is quite clever. They have a weak reference in there, an indicator reference, which is a simple object, and they use this indicator object to see if the garbage collector ran or didn't run. How does that work? Well, you have a weak reference, and if the garbage collector runs, it will simply disappear from memory. So you know if this object is gone, the garbage collector has run. And then you can reallocate it and wait for it to be deallocated again and see if the garbage collector run. Now, Ninject is actually checking that using a timer, and every, I think it was 30 seconds, it's actually checking if the garbage collector ran, and if the garbage collector ran, it would prune its internal object cache and basically free up the memory that it was holding on to and free up the cached objects that it instantiated previously. Now remember, when we looked at how the garbage collector works, it's not guaranteed to run, which means the weak objects or the weak reference we have in Ninject here would never be freed, and Ninject will simply keep the dictionary of cached entity framework contexts around forever until the garbage collector runs. Damn. So we basically found out that Ninject was holding on to all of our entity framework contexts, and there was no really good solution. We found a couple of other people having the same issue, so we decided to get rid of this one for our application and switch to a different one. We did that, and we found that memory usage dropped to a normal level, and we actually fixed the issue there. So by changing the DI container, not to blame the DI container, but just to blame the way it cycles and garbage collects at memory, we found out that by simply changing that and changing the way it behaves, we could actually drop the memory pressure again, and we are now still stable at around 4 gigabytes of memory on our web servers. So yeah, nice. And this time we closed the case, and this time we're actually good for a year and 2 months now, so awesome. So yeah, in conclusion, there's a couple of things you have to do. You have to know your system when you have a system running. You have to know your runtime. You have to know all of the different components that you are using. And I really like the reference that highscalability.com gave us, where they told like profiling and debugging an application is typically similar to the work that an FBI profiler would do on an actual crime scene. You have to sort of gain insight into whatever is happening in your service, get to know it, get to know the life of your service to find out what may have happened in a specific case. And I used to not really like debugging and finding out what was happening with a service, but by doing this, I found out that I learned a lot of things about the .NET runtime, about our own application and things like that, and it's actually a good thing to do. So if you have a service running and you are like me, not really liking debugging it and doing things like that, do dive in, because you will build experience and you will gain insights into finding the source of an issue the next time much faster. With that, thank you for being here, and thanks for joining me in this graveyard shift.